Good morning, everyone. My name is Kadek Diva Sapitri, and today I'm going to present one of the fundamental topics in calculus, which is limit. In this presentation, I will explain the definition of a limit, how limit work, the properties of limit, several methods to evaluate limits as at infinity, and finally some practice problems. I hope that by the end of this presentation, everyone will have a better understanding of the basic concept of limits. Now let's begin with the definition of limit. Okay, next. Okay, on this slide, we will discuss the definition of a limit. A limit describes the value that a function approaches as the input variable gets closer and closer to a certain number. In other words, we are interested in what happens to the function when x gets very close to to a particular value, even if x never actually reach that value. Okay. Limits are one of the most important concepts in mathematics because they are the, the foundation of calculus. They are used to define derivative, which describe rates of change, and integral, which are used to calculate areas under curve. A mathematical notation for a limit is shown on this slide. We read the notation as the limit of f of x as x approaches as equal L. This means that when x gets closer and closer to a, the value of the function f of x get closer and closer to L. It is important to remember that limit focus on the behavior of the function near a certain point, not necessarily at the point itself. Now that we understand the definition of a limit, let's look at an example. Okay, on this slide, we have an example to help us understanding limits more clearly. Consider the function f of x equal to x plus 1. Suppose we want to find the limit of f of x plus x approaches 2 instead of substituting the value 2 immediately. We first examine the value of the function when x is very close to 2. For example, we use the value 1.9, 1.99, 2.01, and 2.1. Next, we calculate the value of the function for each of these numbers. When x equals 1.9, the function value is 4.8. When x equals 1.99, the function value becomes 4.98. When when x equals 2.01, the function value is 5.02. And finally, when x equals 2.1, the function value is 5.2. As we can see from the table, the function value becomes closer and closer to 5 as x approaches 2 from both sides. Therefore, we can conclude that the limit of f of x as x approaches 2 is equal to 5. Next examples show that a limit concerned with the value that the function approaches greater than the exact value of the function at that point. Now that we can understand this this example, let's continue to next concept, which is left hand limit and the right hand limit. Okay, next. Okay, now let's move on to the concept, to the next concept, which is left hand limit and the right hand limit. When discussing limit, it is important to understanding that a function can be approached from two different directions. The first one is called the left-hand limit. A left-hand limit means that the value of x approaches a certain number from values that are smaller than that number. This notation is shown on the slide. We read it as the limit of f of x as x approaches from the left. On the other hand, we also have the right-hand limit. A right-hand limit means that x approaches the number from the value that greater than that number. Its notation is read as the limit of f of x as x approaches of a from the right. From the limit to access both the left-hand limit and the right-hand limit must have the same value. If these two values are different, then we say the limit does not exist. This concept is very important because many functions have different behavior when they are approached from different directions. Therefore, before concluding uh, that a limit exists, we must always check both sides. Now let's continue to properties of limits. Okay, next. On this slide, uh, we will learn about the basic properties of limit. These properties help us simplify calculation and solve limit problem more efficiently. The first property states that the limit of a constant is the constant itself. For example, if the function is always equal to 5, then the limit is also 5. The second property is the sum rule. This means the limit of the sum of two functions is equal to the sum of their individual limits. Next is difference rule. Similarly, the limit of the difference of two functions is equal to the difference of their limit. The fourth property is the product rule. It tells us that the limit of a product is equal to the product of the limit. The fifth property is the quantity rule. The limit of a quantity is equal to quantity of the limit, provided that the denominator is not equal to 0. And finally, we have the power rule. This property states that we can first calculate the limit and then raise this result to the recursive power. These properties are widely used because they make solving limit problems much faster and easier. Now let's learn some methods for evaluating limits. Next. Okay, the first method is called direct substitution method. As the name suggests, the method simply substitutes the value of x directly into the function. This method works when the function is continuous and the substitution does not produce an undefinite expression. Let's look at the example shown on the slide. We want to find the limit of 2x squared minus 4x plus 5 as x approaches 3. Since this function is continuous, we can substitute 3 directly into the equation. So 2 times 3 squared minus 4 times 3 plus 5. 3 squared is 9. 2 times 9 equals 18. 18 plus 20. Sorry, 18 minus 20. Sorry, 18 minus 12 plus 5 equals 11. Therefore, the limit is equal to 11. This is easiest method to evaluate the limit. However, sometimes direct substitution give this give us an indeterminate form such as 0 over 0. When this happens, we need another method that brings us to the next technique. And next, the second method is factor method. The method is used when direct substitution product is indeterminate from 0 over 0. Instead of stopping there, we simply simplify the expression by factoring the numerator or the denominator. After factoring, we cancel the common factor that appear in both the numerator and the denominator. Once the expression has been simplified, we substitute the value of x again. Now the limit is usually be evaluated without any problem. The factoring method is one of the most common techniques in calculus because many polynomial limit problems can be solved in this way. Whenever direction substitution gives 0 divided by 0, always remember to check whether the expression can be factored first. After understanding the factoring method, we can move to another useful technique called the rationalization method, which is especially helpful for function involving square root. Okay, next. Okay, now let's continue with another method for evaluating a limit, which is called the rationalization method, or sometimes known as the conjugate method. Okay, this method is commonly used when the function contains square root. Sometimes, if we substitute the value of x directly into the function, we obtain the indeterminate from 0 over 0. To solve this problem, we multiply both the numerator and denominator by the conjugate of the expression. The conjugate changes the sign between two terms. For example, the conjugate of square root of x plus 1 minus 2 is square root of x plus 1 plus 2. By multiplying the expression by its conjugate, the square root is eliminated, making the expression much simpler. After simplifying, we can substitute the value x again to find the limit. This method is especially useful for a function involving radical because it transforms a complicated expression into a simpler one. Now that we have learned three different methods for evaluating limit, let's move on to limit and infinity. Okay, next. Okay, next is limit at infinity. On this slide, we will discuss limit at infinity. Unlike the previous example, here x does not approach a specific number. Instead, x become larger and larger, approaching positive infinity or smaller and smaller, approaching negative infinity. When evaluating limit at infinity for rational function, we compare the highest degree of the numerator and the denominator. These are three possible cases. The first case it is when the degree of the numerator is less than the degree of the denominator. In this situation, the denominator grows much faster than the numerator. As a result, the limit is zero. The second case is when the degree of the numerator and the denominator are equal. In this case, the limit is simply the ratio of the leading coefficient. For example, if the leading coefficient of the numerator is 3 and the leading coefficient, the denominator is 2, then the limit is 3 over 2. The third case is when the degree of the numerator is greater than the degree of the denominator. Here the numeration grows faster than the denominator. Therefore, the limit approach positive infinity or negative infinity depending on the sign of the leading term. Understanding these three cases makes it much easier to solve limit involving very large value of x. Okay, next is practice problem. Okay, finally, let's look the practice problem. So, on the slide, these exercises are designed to help us apply the concept and method that we have learned throughout this presentation. When solving a limit problem, the first step is always check whether direction substitution works. If direct substitution product and indeterminate form, such as 0 over 0, we should choose another method. For polynomial expression, we usually use the factoring method. For expression involving a square root, we use a rationalization method. For limits involving infinity, we compare the degree of the numerator and the denominator. By choosing the correct method, we can solve limit problem more efficiently and correctly. Practice more equation will also improve our understanding and strengthen our problem solving skill. Okay. Okay, that brings me to the end of my presentation. Thank you so much for your attention. Thank you and have a great day. Goodbye.